Hello and welcome to this low-level JavaScript video where again I have something cool for you. This is actually a continuation of a previous something cool, which was the implementation of the Koi image format, the quite okay image. And as you can see, the specifications sitting open here on the screen. And yeah, so in the last episode, which is well worth watching, if you're coming into this, but I guess you could also just watch this one on its own and then go back and watch the previous one. But in the previous one we wrote an encoder. So what that means is that we can take a buffer of raw pixel values like RGBA values, run them through the encoding algorithm specified by Koi, and get out a Koi file in the end. And that should hopefully be, a nice small file representing losslessly those image pixels. And yeah, so that's kind of one half of the equation, right? Getting something into that format. But of course, we also need to be able to get pixels out of that format so that we can actually display them on the screen. And so that's what we're going to do today. We're going to build the decoder side of things. And then hopefully, once we have the decoder built, we can make a little web page where basically the user can basically upload a Koi image and have that displayed in the browser using the canvas. Yeah, and also I'll probably adapt this little tool that I made, which I made a little tool here to just upload an image into the browser and basically take a hard-coded image and give back the raw pixel values. And I think what I'll do is I'll go in and I'll modify that as well so that we can upload an arbitrary image of like, let's say, a given set of possibilities like JPEG and PNG and a few other different web formats, right, that exist. WebP, I guess. And turn them into Koi files. So that will kind of complete the whole circuit. We can both turn images into Koi files, we can display Koi files, yeah, and we can understand them, which is actually the main goal here. Again, this format was made by designed and spec'd out by Dominik Sabluski. Again, thank you for doing it. It's awesome. Still a big fan. Yeah, let's actually just get straight into it. All right, so specs open here. Let's make that a little bit larger because, yeah, why not? And what I'm going to do is I'm going to open up source here, and we've got this encode file, and I think I'm going to change the name of this. I think I'm going to call this lib because I want to put the encoder and the decoder in the same file because they kind of live together. And then I guess the other first thing to do is to actually extract it, because as you can see, what we've got is like kind of a script that just takes one file and turns it into a Koi file. That's great, but I want to have an encode function which takes a buffer of pixels and turns them into a Koi format. And then we can use that. We can call that from any place, and that's why we're creating a lib, basically, right? We're creating a library thing that we can use, and we'll drive the specific images that we want out from the outside of the library. Okay, so first let's just make an encode file function rather. That's going to take a raw pixel buffer. Yeah, I'm going to call it buffer because then I don't have to change anything else. Which is a uint8 array, and what we're going to return from that is probably just another uint8 array, which will represent the Koi file. We could also return a more descriptive thing than that. Actually, we need a little bit more information to come in here. We need the buffer of pixels, but we also need the width and the height and the number of channels. And yeah, that's what we need. And then in the end, we return a uint8 array. And so what are we going to do here? We're going to take so what have we got here? We've got basically we need to take everything up until here. Just cut that. dump it into this function instead. And there's probably going to be a couple of things we need to change here. For example, yeah, here we're using image height and image width. Well, we'll just make those width, height. Channels is good. This all looks good. I saw another image width and image height there. And let's just delete the constants that I have for those. I see that there are no references for them anymore, so that's good. The only thing we're not doing now is actually returning the buffer. So that's our encode function, looking good. And yeah, let's just check that it still works. It should. There's no reason it wouldn't at this point. So we're going to pass our buffer, the image width and image height. And now I've deleted them. I've actually forgotten what the dimensions were. So let's take a second look. We can figure that out by running file on the original image, which is monument.jpg. It's 735 by 588. 735 by 588, and it's a 4-channel image. We have RGBA. Koi can also encode just RGB images, which is nice. It will treat them. It will treat pixels as RGBA, but it will basically cost nothing to the encoding to do that. And then when you decode, you're going to get an RGBA image out. So you don't lose any information, but you actually might gain some information, kind of redundant information. Okay, so index, yeah, that's the other thing. We can't just return. No, we just need to do the slicing at this point. If you didn't see the last episode, the way that Koi works is it doesn't actually. There's no way of knowing ahead of time what a given arbitrary image, what the size of that image will be after compression. But we can work out the maximum size that image could be after compression. So what we actually do is we pre-allocate a buffer that is that maximum size, and then when we return it back to the user, well, in the reference implementation, I'm actually not sure how that number is passed back. Oh yeah, so in the reference implementation, the return value is like a pointer to the pixels themselves, but you pass in an object which a struct which Koi will also fill out for you, and then that contains the height and the width. And no, that's not actually true. And now I don't. You do that for the encoding, but I'm not sure how that index comes out. But either way, what we can do is we can just slice down the buffer to the index, and then we don't need to expose it to the outside world. There's no reason to have that here. So this should work the same, and I'll just test that out, that it does work the same. I can't see why it wouldn't, but so we'll run ts node source lib, and here we get this encoded Koi. Let's delete that, and then let's run this. Cannot use an import state outside of a module. Import statement outside of a module. I think this is because I changed something in my I've changed something here in my ts config, so that when we come to produce some HTML later, it will produce it correctly. I guess for now what I can do is do this. It's kind of a cop out, and then we'll change it shortly. Okay, so we've encoded, and then what we can do is we can compare that to the, so that's the encoded TS. We can compare that to the reference implementations generated file, and they're the same. So that's good. We haven't broken anything. That's always a good start. Okay, so now we're going to write a decode function, and it is pretty much going to be kind of the inverse of what we've already done here in encode. So when we go to decode, we're going to take a KOI buffer. I'm just going to call it buffer again. So it's going to be a uint8 array. And we will return, from this I won't just return a set of pixels, because we need KOI to tell us what the width and the height and everything was. I mean, we have the information presumably, but what I think I'm going to do is I'm going to create and export a type called KOI format, KOI file, and that will contain basically this other information like width, height, channels, color space, and then the pixels, which will be a uint8 array. So that's it. That is kind of the descriptor, the struct that we need. Except, you know, in the reference implementation, you just get a raw pointer back for that. Ooh. All right. Let's just do this for now, so that we can see when real errors come up. Color space 1 pixels. Yeah. Okay. All right. So beginning here, a lot of this is quite similar to encode. So for example, we need a previous color and we need scene pixels. Those things we're going to need. Don't think we're going to need a run, because that information is going to be given to us. I actually don't think we'll need to make this let either. I think we can do it const, because we won't assign pure. Oh, maybe we will. I'll leave it as let for now, and we'll change it later if we need to. We won't need to, but if it feels like the right thing to do. Yeah, so we're going to have, this is going to be a little bit different, because we're going to be, like before we had like a for loop iterator that was going pixel by pixel. It was very predictable. And now we're going to be pulling bytes out of this buffer, like this KOI file buffer. We're going to be pulling byte by byte, because like sometimes we'll need to read 1 byte, sometimes we'll need to read 2, sometimes we'll have more or less stuff to do there. And so I think what will be easiest will simply be to create a read index, I'll call it, and a write index. So we're going to be reading from the buffer and we're going to be writing into like a pixel buffer. So let's make a, don't know how big to make the pixel buffer yet, but we will in a second. So in encode, we also have this nice function write32. And we're going to have, I guess we'll just write the opposite function here, which will be read32. We don't need to take any things there. And what we're going to be doing here is, instead of, you know, filling up some values here, we're just going to read stuff out of the byte array. So this is going to be called buffer. It's going to be the read index that we're adding, and we're going to be doing some shifting as well. So for example, we're going to yes, every time. Wouldn't be a good episode if I didn't do that every time. So I don't want to have those on the side. It's like excessively picky, but so unlike yeah, as I mentioned in the last format, and as it clearly mentions in the spec, the magic number, the width and the height, they're all encoded big endian. they all have big endianness. And so when we read them out, we need to make sure that the first byte we read gets pushed into the high spot. So basically, this doesn't even make any sense anymore. What I'm doing here, we're gonna make a 32-bit number, but in order to do that, we have to take this byte and then shift it up by 24. And with these ones, we have to shift them up by these amounts. Yeah, so we take the first byte, we shift it up by 24 bits, so it's like represents the top byte of a 4-byte 32-bit word. Then we OR that in with the next byte, which is just pushed up to the next position, and so yeah, that's how that works. So now we've got to read 32. Now we can actually read the header, which here we have in the spec. So first we have the magic number, should be coif. Yeah, so let's do it like that. So what we can say is, first of all, if read 32 is not equal to the magic number, and that magic number, this is, you know, the characters, ASCII characters coif, but I've already worked out what that is as an actual number, as a 32-bit number, and it's this. So if we don't read that, then, you know, something went wrong here. So let's just throw an error, throw a new error, invalid COI file. That's it. That's enough. So we don't know for sure it's a completely valid file at this point, but we have some idea that it should be. I guess we could be a bit more extensive than this. We could check the magic number, but first we could actually check, like, does the file meet a minimum number of bytes that it should be? So if so how can we do this? If buffer.bytelength is less than, and the minimum number it should be is the COI header size plus the COI end marker size. It should be at least that big, right? Even if it doesn't have any pixels inside, it should be this big. Then let's just throw an error at that point as well. Once we know that there are enough bytes to actually read something, then we can actually again go in and read the magic number, and if that's not right, then we can throw an error. Then we can actually get the width. And the width is going to be just read 32. The height is also just going to be read 32. The number of channels, which is the next thing in the header, that's going to be just reading a byte. And I might actually make a read byte function, even though it's like a super simple operation. Just because we're going to do it so much, and it's kind of nice to have the descriptive way, right? I mean, it's like optimization wise, it's not, you know, it's not the best thing to do, but because yeah, you create a call stack and everything, and that's an unnecessary function call. And unfortunately in JavaScript or TypeScript we can't do stuff like you know, inline or always inline, which would be cool if you could do that, but you can't. So width, height, channels, and color space. And color space doesn't do anything in this, like in the format itself, but it should only have 2 valid values. Channels should also only have 2 valid values, which would be 3 or 4. So you can either have RGB or RGBA. I keep going back to this thing in the specification, which is that the color space and channel fields are purely informative. They do not change the behavior of the encoder or the decoder. Well, in the encoder, you kind of do need the channels, because you need to know how many bytes you advance through the pixel buffer as you go, because if you have 3 bytes, it's different to having 4. Maybe there is an expectation that they're always RGBA, but the A does nothing. I don't know. But yeah, here we're also going to need to work out the buffer. Let's call it the pixel buffer, just to not get too confused. So the pixel buffer size here, width times height times channels. I'm just going to assume that we get the right number of the right channels, and that color space has a valid value and everything. This will be unused as well. We're not going to do anything with it. Oh, we will return it. We should have values for those now. Then we can make it a pixel buffer. So then we've got a pixel buffer, and yeah. Now we could actually start iterating through. So what we want to do, I guess, is to say while the right index is less than the I mean, I'm sure there's ways that like an invalid file could bite us here. Let's base this on the read instead. So if the read index is, like, while the read index is less than the buffer dot byte length minus the COI end marker size, right? So we just ignore the end marker. We assume that we get a valid end marker. We're just going to start reading bytes. So hopefully this should make it that we don't get into any infinite loops. Even if we end up generating a weird result at the end, we shouldn't get stuck in this function. All right, now we can just start pulling bytes. So like, we're going to go byte by byte, and we're just going to look and see which decoding strategy we need to use, which chunk we're dealing with. And there are a couple of different possible chunks. There are like 4 categories of chunks. Run of pixels, an index into a hash table of pixels that we build up as we go along, a difference in RGB, and that can be either a difference in just a regular difference or a luma difference, or a full RGB or RGB value. So in those cases, we just have RGB encoded in 3 bytes or RGBA encoded in 4. And we need to tackle these decoding strategies in a particular order. And actually not in a particular order, but we need to check the 8-bit tags first, right? We have 2-bit tags for these strategies. So these show us which strategy we're dealing with. But we also have 8-bit tags for when we have full byte values, full pixel values. So we need to check these ones first because they collide with the 2-bit tags, and yeah, you would get the wrong result otherwise. So let's just read a byte. And let's add some more of these constants up here. So we know, for instance, like an RGB operation or an RGBA, we have already those. We already have those here, so I actually don't need to make anything new for now. What we can say is if the byte is actually equal to the COI op RGB, that means that we just have pure RGB pixel, RGB value. And then we need to read 3 more bytes, as shown here. We've read this byte, and then we need to read red, green, and blue. Sorry if my microphone is picking up that annoying vibration sound. I've got a new phone, and it's got a very loud vibration setting. yeah, so we can get the R value, which we can do by reading a byte. Read byte, G and B. And then we're gonna write that to the buffer, right? That's pretty straightforward. So what I might do here is we've got these two functions. I might actually make a write. I'm gonna make a write color function. Write color, which takes a color C. And what it will do is it will take the pixel buffer, which we should have defined above, but have not. So yeah, we need to write that function down here to avoid having not seen that yet. And we'll get the write index, and that's going to be C.R, G, B, A. So that's going to make life a bit easier for us because we can just pass this a color and it will advance the write index and it will just write the color value in. We're only ever going to be writing color values. And what that means is we can, instead of doing this, we can say previous color dot R. So we're setting the R, G, and B values, but we're going to use the previous alpha value. And the previous color is a value that the encoder and the decoder start with. And in this case, it starts as black, but most interestingly, it starts with an alpha of 255. So, of course, that's an extremely common alpha value. And the fact that like the encoder and the decoder know that means that it doesn't even have to live in the file itself. That's like fully compressed out. So if you're just dealing with RGB pixels, which are all full alpha, then you don't even need to worry about that. So what we're doing here is we're just overwriting RG and B because this is going to be our new previous pixel anyway. What we can do is we can just say write color, prev color. Cool, that's that. And do we need to do anything else here? Yes, we do need to do something. And the something that we need to do is that we also have this scene pixel array, which acts as a hash table. And there are 64 entries in here, and we have a hash function, which is specified in the specification, which is this function. And this will produce an index into that table. And what we have to do is every time we see a new color, we are going to put it into that table. And that's what the encoder is expected to do as well. Like every time it encounters a pixel value that it hasn't seen before, it has to put that into the table at a given position. And seeing as we're using the same hash function, the pixel should end up in the same place, and therefore, yeah, this should work out nicely, even if you have collisions. Right, so that's good. We write the color, and then we need to say scene pixels. Scene pixels. Why don't we make a function for this as well while we're here? We already have the right color function, so let's insert color into scene, Seeb. So we will compute the hash function, which we already have elsewhere. It's going to be C dot, missing the 4 on the end there, and then we're just going to say scene pixels at that hash equals, I'm going to make a copy of the color just in case we get into any funny business there. So we've seen this color now. Let's insert it into the scene table, and then we can just continue, right? Jump back to the top of the while loop and grab the next byte. RGBA will be basically the same thing. only we need to actually overwrite the alpha value because we now have that, but we're still going to write it and we're still going to insert into the scene. So 2 strategies taken care of. Okay, let's go from kind of the simplest to the most complex. So the next simplest thing is the run, which basically we have 1 byte, which tells us that there's a 6-bit value which can be 64 different values. We have a 6-bit value here which tells us how many times we've seen our previous color. That's it. It has a bias, so when we encoded it, we did a subtraction of 1 on the value, and that means that, well, the reason is if you have a run, and if you have a run, it means you have at least 1 pixel, right? You have at least 1 copy of the previous pixel. So the value 0 doesn't make any sense, and the way that this allows you to not lose 1 position because of that is that you bias it with -1. So that means that a run of 1 is basically, this would be a value of 0. Yep. Probably over-explaining obvious concepts here, but just so we're all on the same page. Okay, so to check the 2-bit tags, it's a bit different. We don't have the tags. Yeah, these are the tags, right? So so what we need to do is we need to take the byte. Yeah, let's do it like this. We want to isolate those 2 bits for each possible tag, and so we're only ever looking at these 2 bits and comparing them. So we want to make a kind of mask, and let's call it the Koi. I don't want to call it Koi op mask because that would be confusing. So I'm just gonna call it chunk mask. Yeah, that's fine. And the mask is actually going to be C0 because that is a value of 11000000. So that will allow us to isolate those top 2 bits if we AND another value with that. And then we can directly compare it to the tag. So we take the byte, we AND it with our Koi chunk mask, and then we check if that equals Koi op run. And if it does, we know we're dealing with a run. And how do we get the run value? Well, that is in the bottom 6 bits. So that's the kind of the inverse of this chunk mask. Make a new constant here, call it Koi run length. And so yeah, what we want is that the bottom 6 bits are 1s. That's going to be 3f. Yeah, that's 3f. So we can get those. We can get the run length by taking our byte and ANDing it with the Koi run length. But we need to add 1 because it was biased with -1 before. Now we need to unbias it, get the actual value, and then we can just do a for loop where we go over that many times. So and we're going to write the previous color, so it's great. All we need to do is write color with previous color. And we don't need to store previous pixels or anything because we know we've seen this pixel before because it's a run of the previous pixel. So continue. That should be the run strategy done if I haven't messed anything up there. Don't need to put in the hash table either because it's implied that we would have seen it before. Okay, so what's the next simplest thing? I think the next simplest one would be the index. So let's check that. It's going to look pretty similar to this. So let's do that. Koi op index. Okay, so like you can see, the index is also in this top 6 bits. Bottom 6 bits. No bias. And yeah, that's it. So I'm just gonna, I know it's the same constant, but I'm gonna make another one that just says that this is where we get the index. Just so the code is clear. Const index equals the byte ANDed with koi index. And then the color is the scene pixels at that index. And then we can write the color. And again, presumably we've seen this pixel before, if we're doing this encoding. So that should work. Great, so we've done 4 of our strategies. How many strategies do we have total? 6, right? So we just have the diffs left now. So the first diff is simpler, so let's do that one first. Yeah, it's going to look pretty similar to that. If we have a diff. Okay, so we need to pull 3 values out of the diff. And they are in 3 fixed positions. So that is the difference in red, the difference in green, and the difference in blue. Let's make some constants for that. So const koi dr. Let's call it diff red. Yeah. So though that is in bit 5 and bit 4, so that is going to be what's that? Is that 30 in hex? Let me just check. X30 48 string 2. Yeah. X30, and the difference in green, that is going to be like 2 down. So what are we looking at there? It's going to be C, right? Yeah. And then difference in blue is a bit easier. It's just 3. Cool. Yeah. So we get our difference in red. Just call it dr. We get that from taking the byte, ending with koi diff red. And these are all biased with -2, so we need to add 2 to these. Difference in green. Difference in blue. Yeah, so these are differences from the previous color. So what's going to be the easiest way to do this then? This isn't the color, obviously, right? This is the difference. And that means that what we can do is we can say the previous color dot red equals previous color dot red I guess we add, it doesn't matter, we need to just do an add here because it will get a negative number potentially. And what I'm going to do is I'm going to do an AND FF here. And why am I going to do that is because, well, these are just regular JavaScript numbers, but in reality, these are actually byte values. And so what you can imagine is that we would potentially, like, we can encode differences that kind of go around in a circle. Like, so if you have when if we're encoding the image and we have a red value of 255, and the next pixel has a red value of 0, there's actually only a 1-bit difference between those. Or there's only one value difference between those. Even though it crosses this boundary, right? It goes like sort of over the boundary. But we can handle that by doing this, right? Because this will basically perform an addition that ignores the carry bit. So yeah, so this would work, potentially. Hope that's clear. G, we can do the same thing for G, and we can do the same thing for B. And yeah, that should be G, and that should be B. So we've got a new color. We actually have the color value now, so let's write that. Write color, prev color. And this is a new pixel. This is a new pixel value because it's a difference to something we've seen before. So that means we need to put it into the scene pixels. So let's insert into scene, prev color. All right, that's that one. And now the last strategy, the luma difference. I think it's going to be pretty similar. So I will copy that. It's pretty much the same thing, but with a little bit more in depth because we need to do a couple of calculations to get the red and blue channels. So the difference in green, well, let's take a look at the spec here. So what you can see is this is actually encoded in 2 bytes. And in the first byte, we have the difference in green is a 6-bit encoding, which means we can represent a much larger set of green differences, right? We're not limited to 2-bit differences as we were before, which only gives us like 4 possible values, like 2 back and 1 forward. So here we actually have a 6-bit green channel, and so we can represent differences between -32 and 31. And with the second byte, what we actually encode is the difference in red minus the difference in green, as long as that number fits in 4 bits. So yeah, it's a little bit more involved, but not that much more. So first things first, we need to add some constants. So the Koi Luma green. The Koi Luma green. Well, that's just a 6-bit value, right? And we already know that is 3F because we've done that for the run length and the index. The Luma red, that is the top, well, it's not the red, it's, I'm going to call it DRDG, because it's the difference in red minus the difference in green. That is encoded in the top 4 bits, so that's just F0. And then the difference blue, difference green, well, that's just encoded in the bottom 4 bits, so that's just 0F. Yeah, cool. So we can get the difference in green by taking our byte and ANDing with Koi Luma green. Yes, and then we need to add the bias, so we add 32 for the bias. Okay, and then we actually have a like the second byte that holds all the rest of the information, so let's just make byte 2, which is just read byte. Yeah, byte 2, and then I'm going to call that DRDG, DBGG. That's going to be byte 2, and then Luma, yeah, and that's going to be DRG, and then just change that one. And these are offset by 8, not by 2. See, in the thing we have 4 bytes, so 4 bits, so we said offset it by 8, because that is the bias that is spoken about here. So, given these values now, we can actually calculate the dr and the dg. So the dr, well, that's just it's the actual difference in red is minus the difference in green. So we can just add the difference in green to this plus dg, right? That gives us it back, and then that's it. And the difference in blue then is the same thing, but in blue, and then again we just do this same operation where we allow over or underflowing. This would work also with underflow, by the way. Then we write the color and we insert it into the scene pixels. I think that's right. I mean, that something definitely could go wrong in this. I might need to do a bit of debugging, but I'm gonna venture that might work. So what are we gonna do now? We can test this in this main function here. So I'm gonna go monument.coy, because that's a known value that the reference implementation generated. So we're gonna read that. We're gonna get a buffer. We are gonna decode the buffer. That is going to give us a COI file, and then what we can do is write that out as decoded.ts, and it's not bytes, let's call it COI file. COI file.pixels, we just write the pixel values out. It should be right. If that works, then we'll be able to compare it. So let's try running this. No errors. We got a decoded bin, and we have a decoded bin in the same directory, so we can actually just do a direct comparison of those two. Decoded TS bin is size 0, so something. Oh, yeah, that'll do it. Pixel buffer. Try that one more time. They're the same size, that's a good thing, but that wasn't too hard to do since we generated a buffer of that size in the beginning. So let's run compare on decoded.bin and decoded-ts.bin. There is a difference. The difference is on byte 33. Alright, let's take a look. Let's see what's on byte 33. So, what is byte 33? 33 in hex is byte 21, and I'm going to have to do it in this terminal, which is fine. Bewitched, decoded ts.bin, byte 21, so that's here, 94, okay. So what's 94 in binary? 1 0 and 1 0. That is going to be a COI luma. So probably we messed up the luma. Yeah, very possible. Very possible. The nice thing is we know what it should be, and therefore it shouldn't be too hard to figure out. Okay, so how do we do this? We are taking the byte and we are ANDing it with the green value, which is 63, which should be right, and then adding 32. Presumably this is the first luma value. Yeah, we should be able to see that by looking into the right pointer, so I'm just going to... I'm going to debug this. Alright, and where are we on the right index? 64, which should put us on pixel 16. Hard to know if that is the exact... Well, where are we? Yeah, wait. So... 64, but no, we had a problem on 21. Does this make sense? I'm confusing myself here. Because we had a problem here. And we're not that far in yet. Yeah, it's 32, so we're not quite there. So that could mean that the... So if... What I'm thinking is, if this isn't the first luma that's going wrong, then probably it isn't actually the luma, and it's more likely to be something to do with the way we're putting it in the lookup table. That's my instinct, because if we're getting a difference in this pixel, everything else works the same. So these first, this is 1 pixel, 2, 3, 4, 5, 6, 7, 8. Wait. Oh, this is the pixel difference, but this is actually the indicator of which kind of pixel. No, this doesn't make sense. I'm getting myself confused here. What I want to figure out is when this particular pixel goes wrong, like which operation were we on, and we can only figure that out by looking at like the yeah. So what I'm going to do is I'm just going to maybe let's put a breakpoint on here and say when the right pointer, no, I keep calling it the right pointer, when the right index is equal to, and again, what was it? It was 21? Yeah. No, 32. Wait. X21. Yeah. Okay. So that doesn't seem to happen. It's weird because the program's not exiting, but it's also not stopping here. Okay. Right index. Wait, so what was I looking out for? I was actually looking out for I was looking out for 33, so I've already missed it. But fine. It goes quite quickly then. So we do 4. And we get here to 32. So at this point, we're in a regular diff. Okay, so this could be something going wrong here. Let's double check. So in a regular diff, we have an offset of -2, so we should be adding 2 to get to that. It does appear that we're doing that. Difference in red. Red. Well, let's take a look. What are we getting for these values? Let's just run through it. So red, green, and blue. Here we get a difference of 18. That doesn't make any sense. I know what the problem is. Yeah, so these numbers, they need to be shifted as well, right? All we've done is isolate the bits, but they're still in the positions that they are, and they need to be shifted down into the correct positions, which I didn't do. So yeah, so the red value needs to be shifted down by 4 pixels. The green needs to be shifted by 2, and the blue doesn't need to be shifted. Ooh, not too far. All right. Let's optimistically say that that might be enough. Let's run TS Node again. Let's run compare again. Okay. Well, it's like that was a problem for sure. It's also going to be a problem in the Luma for sure. So let's fix that. We don't need to shift that down. This one needs to be shifted down by 4. And this one doesn't need to be shifted down, but I'll put a shift in there just so they all line up correctly. Doing it before I add the bias, so that's good. I mean, that's a problem right there, so maybe that... Still a byte 33, that's incredible. Okay, let's see where we get to. 32, alright, so... a difference of 3. 3 and 3. I'm now thinking values are stored with a bias of 2. Oh, okay, so I've done this the wrong way around. So, like, this should be subtract. These should also be subtract, all of these. Yeah. Continued optimism. We got a different place that this is wrong now, so that's good. Byte 53. Let's see what that is now on. So 4, 32, 36, 40, 44, 48, 52. We had a difference on 53, so likely... Okay, so this is on a run. Okay, what's the run length? The run length is 1. So we end up just writing the previous color, which, what's our write index right now? Write index is 52, obviously. So let's see what we were expecting. And then maybe we need to see what the previous color was. Okay. So Bewitched, let's go in assets, monuments. Oh no, I guess it would be just decoded.bin. And 53. Just run this just so I can use it as a scratchpad. 53 in hex is 35. So that's going to be here. So then we have 4F, 8D, A4FF. So that it does appear to just be like a repetition of the previous pixel, as this was the previous thing, and it's again the same here. What do we see here? 35? Yeah, for some reason that's writing something different in. Like it appears that this, it appears to be a diff of 1, right? So let's yeah, so somehow (52). So we have our previous color here. I need to add a feature of being able to look at the ASCII values, not ASCII, but the numerical, like decimal numerical values in into Bewitched. I had planned on doing that and I just haven't done it yet. So yeah, so we're writing this color 255, 163, 140, 78. That should be the same as whatever the previous color was. Did we actually write that color before? Are we updating the previous color correctly? In the Koi index? Yeah. Okay, if we do an index operation, we're not setting it as the previous color. That's a problem, right? Previous color dot r equals color dot r. So that's GBA. Yeah. All right. That's definitely a bug. Okay, still erroring out here, so that wasn't the problem, but that is a problem here. This is getting properly set as the previous color. This too. RGB, 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 yeah. And then here, RGB, RGB, RGB. This doesn't need it. This is, of course, just setting up the previous color. Byte 53. Just want to check again that I did that properly, right? 35, yeah. So have we done the same thing here? It's so strange, like it knows like that this is the previously written color. I'm interested to see what like what we're doing just before we do that. Okay, so 32, 40, 44. So it's a run. A run of 1. Previous color here. Great. Then we're up to 48, so this is the actual one I want to look at, which is an index. So here we end up grabbing the index 31. Then we get the color there, which is this number. We're writing that color into the buffer. We're setting the previous color values. Continuing. And then here we have a run of that same color. Run length of 1. And then we're writing the same color. So I mean, I just don't see how we're writing a different color this time around. It doesn't make any sense to me. I don't see how we can be getting something different here. Yeah. Really, really confusing. Wait. Now it's not the same value anymore. Or rather, it is the same value anymore, and it's not the same as what it was before. Did I just not run the... Did I just not run the command again after that? Okay, well... that was an interesting series of bugs there that came into play. Not even just one, but quite a few. But at this point, the images actually compare correctly, so that is really great. The decoder works. Excellent. And now we can really prove that the decoder works by actually creating a little a little web app just to do that. So what I'm going to do is I'm going to export these two functions from this little library. Export. We don't need the main function anymore to drive this, which means we don't need the imports there. We can export color. Why not? We could export all of these constants as well, but we don't really need to. So that's it. That's the encoding and the decoding library. And let's actually, from this point, let's build a little page where you can press a button, load an image file in, like a binary file in, a KOI file. A KOI file into the page and actually have it render with the canvas using the debug logic we just wrote. Not the debug logic, the decode logic. All right, so I'm gonna do that by. I'm just gonna put an index page in here. I don't want to mess around with bundlers or anything. So what I actually want to do is I just want to. Yeah, let's call this decode.html. And this is going to be display KOI file, render KOI file. Let's call it KOI renderer. What are we going to have? We are going to have an input. It's going to be upload image, and the type of this file is going to be file. Upload KOI image, and we can put a filter on this as well, right? Accept.KOI. So we only accept KOI files. Let's move that into the label there. And then what we want to have as well is a canvas that we'll use for the rendering, and that will be canvas. We need to give it an ID. What do we call this? KOI renderer. And that's it, right? We don't need to give it height or width because we don't know those values yet until we do the upload. And then in source, I'm just going to write, like, I guess, a script here. The source of which will eventually be dist / render.js. And we're going to say that it has type module, and then that way I think I've done this correctly. Type. Am I doing this correctly? I thought it was type. Here this says I'm type module for HTML compliant browsers, treated as a JavaScript module. Okay. Good. I think that will work. Now, yeah, this is actually why I messed around with this tsconfig, because I want this to just produce an ESNext module. Produce it into the dist folder, and then what we can do is we can write a, what do I call it, render.ts. We can import decode and probably KOI file from lib. And yeah, what we're going to do, first things we're going to do are grab those two elements that we know are on page. So we have ourselves a canvas, document.get element by ID. The element ID, which I've already forgotten, is KOI renderer. And we can say as HTML5 canvas element so that we get proper type information. Otherwise this would just say it's an HTML element. It's not really helpful. And this is going to be the file input, and that is upload image. I'm not great ID names, but and that's going to be a HTML file input. I might need to look some stuff up for this because I don't remember the specifics of how to do this. And I've done it before for another project, and I have it ready to check out. But yeah, I don't remember the specifics. Okay, so yeah, what we're going to be doing is we need to write some event handler listeners for the file input, so that when we actually upload a file, that we read the file in and that we are able to get the bytes out. And then we're going to have something that actually draws to the canvas. So let's write the drawing to the canvas part first. It's going to be draw koi. Yeah, calling it draw koi image would be redundant. Yeah, koi, which is going to be a koi file. So that's what we get out of the decoder. And yeah, so we're going to say that the canvas dot width equals koi dot width. The canvas height will be the same, and we need a context as well. So let's do that. Context canvas dot get context. Whoop. 2D. So yeah, we can create image data. Yeah, so we're going to create image data from the context, and we need to supply that some information. Which information do we need to supply? This start width, start height, I guess. 0, 0. We don't have any special settings. So yeah, we have a koi file. So what we actually want to do is do image data dot data. So that's the actual raw pixel values, and then we can just set that data, and it should be correct, right? Because we're creating image data for this context. We've already preset the height and the width of the canvas. So this image data should contain the right number of pixels for us to inject in there, as long as, you know, the koi file wasn't lying. So then we can just do koi.pixels, set those pixels into the data, then ctx.put image data, 0, 0. That's that. That should be all we need to do in order to draw the pixels. And now we need to drive that function from the file input itself. So how can we do that? We need to do document dot not document, I guess file input dot add event listener, and we're going to do a change event. And yeah, this might be where I need to do a little looking into my old code. So let's zip over to the browser. This project is Spellboy. It's a Game Boy emulator that I worked on some months ago. It's been a while since I've worked on it, and I want to pick it back up again. But yeah, kind of got a bit I got distracted by some other stuff, and I've kind of unfortunately left it behind. But got pretty far with it. Just need to add audio now. But yeah, what I did do was allow the uploads of ROMs inline. So you can just upload a ROM file here. And yeah, it's basically this function which I'm looking for here. So when it changes, we get an event. Made this an async function, didn't need to do that. We create a reader. Let's just copy this stuff. Go back to the code. So we create a reader, which is a file reader, and then we add an event listener. And I actually think I spotted a problem with this code, that you would leak memory if you didn't remove this event handler afterwards. So let's do that. Reader event handler is this, and the event is going to be something called a progress event for a, was it a file? For a file reader? I guess, yeah. Yeah, that's right. We get a progress event for a file reader. I guess that would be invalid KOI file in that case. And otherwise, we call load with our thing. Well, we actually want to call draw KOI, and that's not true. We need to run decode first. So we get our KOI file. We get that by calling decode on the buffer. So we need to do this. We take our result of like when this basically like we're going to be adding a load event. So when the file reader is finished loading the content, it's going to call this handler. We're going to take the result, create a buffer from it, pass that to decode, get ourselves a KOI file out, and then we can call draw KOI with our KOI file. And that should work really nicely if that is correct. But we don't want to, like, we need to remove the event listener afterwards, right? That's kind of the weird thing that's happening here that's memory leaky, is that because we're doing this every time we change the file input, we're adding an event listener. We definitely need to remove it, otherwise we're just creating them again and again and again and adding more and more. So that should work nicely, and then we want to read as array buffer, and then it doesn't need to be E input. We actually have this here, so we shouldn't need to do it. Just whatever the first file is that we selected, we should only select one. I think you can actually limit the number that you select, but hey, for now that's fine. TSC to compile the TypeScript into JavaScript, that seemed to work okay. So in dist we now have a render file. Looks good. We've pulled that in from here. I think this should work. So there is an HTTP server module already installed on this project, because I use it for a tool as well. So let's run that, and let's go back to the browser and get on over to 127.0.0 8080, and then we'll go into KOI renderer. Okay. I'm aware that you're not going to be able to see the file dialogues. I realized that after the last episode because of the way that I have OBS set up. If you know about OBS and you're using like a window capture mode, I would love to know if there's a way to also capture like the child windows that generate from that, so that I could do things like capture the file dialog. I don't want to do a full screen capture. I just want to capture one window. So let me know if you know that in the comments. Otherwise, I am actually trying to grab the file now. I'm selecting encoded TS KOI. So it's the KOI file already made. And seeing as I don't see that now on the canvas, I'm going to guess it didn't work. So let's see, did I mess something up here? Loading module dist lib was blocked because of a disallowed MIME type. Have some idea of what that might be. I think that render, yeah, it doesn't insert the file extension on here, which it needs to do. I wonder if I can make that explicit by doing this. Oh, that's going to tell me I can't do that. Why can't I do that? An import cannot be end with a TS extension. This is probably something in the TS config. I'll do the world's quickest Google here, and if it doesn't work, then I'm gonna just insert it by hand. But TS config generate JS file extension import. Let's take a look. Surely someone's had this issue before. It's not just related, it's the same. Okay, so that means it's this. Just a comment. I don't see. Okay. Oh, it's one of those nice spicy issues where instead of helping people out, they're just getting into a nice argument. Script module. Check this out. Isomorphic browser workflow. I just want the imports to work correctly. I feel like it should. Yeah, but how can I generate this from the tsconfig? Alright, I feel like I've done my due diligence there, and I'm going to just check here to see. It's like file extension, something like that. Generate. List files, file. No emit. Preserve. Da-da. Yeah, use. Yeah, this is I don't know. It's kind of tricky here. Like, I feel like it's. Yeah, maybe I've scrolled past something. I don't know. I will figure that out, but I'm not gonna waste your time by doing it now. So I'm just gonna stick a .js on the end of that, and I think that should be enough to fix it for now. So let's open up the thing so we don't get a cached result. Let's really force a change. Try this again. Oh, something. Let's turn off dark mode here because it should be like that. Let's see. Create image. Invalid width or height. Okay. Let's put debug point down in here as well. Yeah. All right, refresh. Hard refresh. Okay, so we get here the Koi file. Well, it's got the right width and height. It's got the right number of channels. So let's see what's going wrong. Canvas width equals Koi width. Is create image data, is that height and width? I thought. Because if I do that, then it's telling us no. Okay, so something went wrong. Invalid height or width. I guess I need to pass it. I guess I need to pass it a width and a height there. Fine. Draw Koi. Image data. SWSH. Yeah, I guess it's width and height. So let's just do Koi.width. Koi.height. Alright, let's rebuild that. Probably need to go in and change the extension again, annoyingly. So let's put JS in there for now. And let's switch back. Hard refresh. Let's close that up. Excellent. Alright, so that's it. I think I'm going to leave it there for now because... yeah, like taking a file and actually taking like a JPEG file and converting it into a Koi file or a PNG or something. That code is kind of already there, and this episode is already long enough. If you want to kind of play around with that, there is a file in here called tools, image to byte array, and it basically hard codes an image in here, which can be a JPEG or anything that can be drawn to the canvas, and then draws it to the canvas, and then, you know, basically automatically downloads it. But what you can imagine is injecting the encode in here, you know, pulling in the encode library, encoding that, like drawing the image to the canvas, pulling the data out, encoding it as a Koi image, and then allowing the user to download it. So that's something you might want to play around with. But I think I'll leave that for now, and then we can just see this here, this beautiful representative image, which was my example image from the previous episode, if you saw that. It's well and truly drawing and decoding a Koi file. So I think that's a win. I'm really enjoying making these binary file and this kind of getting into this kind of stuff. I've wanted to do this for a while, making more of these kind of episodes, more standalone kind of content where we just explore something interesting. And yeah, I think people also like this kind of stuff too. So maybe I'll do some more of these, looking at some other kinds of file formats. Obviously I did WAV in the past, and that was a lot of fun. Yeah, let me know down in the comments what kind of binary files you'd like me to take a look at and unpack and, you know, write parsers for and encoders for, and yeah, let me know. Anyway, I hope you have a great rest of the holiday season, or if you're watching this in the future, just a great day, I guess. I'll see you next time.